Okay, so if, I did 4.2 earlier, but somehow it disappeared. So I'm just going to jump straight to the problems. And essentially all it's saying is that you can find the critical points if you find the derivative equaling to 0, and that in some cases there is no critical point. So I'll give you an example. For cubic, a perfect cubic, y is equal to x cubed, you're going to discover the derivative is indeed 0 here, at 0 comma 0. And however, that's not a max or a min. It's definitely sort of a turning point, but it's not a max or min. You're also going to discover that in some situations like this one, which is a parabola, that if I take the absolute value of this parabola, it's actually going to have a bottom part that's like this. And it's going to be have these very sharp turns. Well, you won't always be able to find the turning points at those points. So they're unique situations as well. They're called cusps. And then also of the absolute value itself, you're going to discover interesting things. So the point I'm making, though, is they want you to make sure when you're dealing with a maximum or min. And later on, we're going to learn that the second derivative is really useful for that. But in the meanwhile, they're going to want you to sort of test what's happening on either side of the max or min. So let's get right to it. Okay, number one, explain. Well, when you set the derivative to equal to 0, you're finding when that slope is equal to 0, and thus the only time that slope on a graph is 0 is when it's got a critical point or a turning point. Explain how you would find the critical point. So I urge you to always examine your graph before you start. Okay, and you should look closely at this first and say, okay, I'm dealing with a cubic, but I'm also dealing with a cubic where I can find the some of the x-axis points, which means I'm dealing with this cubic here that goes through 6, 0, which is there, and 0, 0, which is there. And because this is squared, I know that it turns. It touches the 0, 0 and turns, comes back and up. Well, just knowing this graph right away from this information is helpful, because I'm going to be able to know that there's supposed to be a local max there and a local min there, and that local min's probably at 3 comma 0, but not 3 comma 0, but 3. But in any case, understanding what I expect to find is really helpful. So first thing you do is take the derivative. Then you set it to equal to 0. And you can do the same thing here. You'll notice that 3x comes out of both of them. And you get x minus 4 is equal to 0. And there I've discovered that it is indeed not 3, which is good, but it's in an expected area, 4. So it's over here at 4. So I've discovered that this slope is 0 when x is 4 or when x is 0. Well, I expected that one, and even putting it into the formula, I discovered that indeed 0 comma 0 is a local max. And I know it's a local max just because I know cubics always start in quadrant 3 and end in quadrant 1 when they're positive in front. And this one's a positive number in front, positive coefficient. Therefore, since this point is first, it must turn, that must be a max. For instance, I could not come here and then somehow come back to that point. This line is impossible for a cubic to go to this point here and then come back and then go up. So since I know what the graph should like, I can immediately deduce without any further knowledge that this is a max and this is going to be a min. However, if you didn't have that information, you would immediately take the slope immediately to the left, so minus 1. And if there's a positive slope there, you'll know it's a max, especially if there's a negative slope over here at positive 1. So putting negative 1 into this, I get negative 3 times negative whatever it is, 7, and that comes out to positive 21, which means there's a positive slope on this side. Putting 1 into here, I get 3 times a negative number of negative 3, which is negative 9, which means there's a negative slope here. And that automatically tells me that that's a max. Later on, you're going to learn that if you take the second derivative, okay, so if I take the second derivative, so that's first derivative, second derivative will be this, and I put the 0x into there, if I get a negative result, we're dealing with a max. So sure enough, 0 minus 12 is equal to minus 12. So that's a negative, and I know that's a max. So I might as well show you that now because it's useful. The other useful thing about second derivative is it's going to teach you inflection points. The inflection points happen when this is equal to 0. So 6x is equal to 12. So x is equal to 2. So right here at 2 something, 2 comma something, if I put the 2 up in here, I'm dealing with 8 minus 24. I'm dealing with minus 16. So at 2 comma minus 16, I know there's an inflection point. That's where the slope suddenly goes from getting more steep to less steep. That's what an inflection point is. And there's only usually one inflection point in a cubic, so there's 2 less than the degrees. So that aside, I'm now going to look at this 4 value. So when we plug in 4 up here, it's 4, and when 4 goes into there, I've got 16, 64, 256. So 256 minus 416 times 6, 36, 96. So those are off. So I'm talking about 4 comma 160. So then now I know that's wrong because I know it's got to be negative right here, right? So we'll try it again. 4 cubic, so I made a mistake on that. 4 cubic is actually 64, and then it's minus 96, so indeed it is minus 32. So right away, because I knew my graph, I knew it got the wrong value. So then we're dealing with 4 minus 32 is the max, or is the min rather, right there. And also if I take my second derivative, which was so here's my first, I accidentally erased my first derivative. So my first derivative was 3x squared minus 12x. And therefore my second derivative is 6x minus 12. And if I punch in a 4 there, like I said, you get 24 minus 12. It comes out a positive 12. And that positive on the second derivative tells me that I'm dealing with a minimum point. So it means when the second derivative for that x value comes out positive, you're dealing with a min. When the second derivative comes out negative, you're dealing with a max. And when the second derivative is set to equal 0, you can find the inflection points. I might as well tell you all that now. It saves you a lot of time. Determine the critical points, we did it, and then sketch the graph, we did it. Find the critical points for each function. So I'm going to also do the second derivatives here. So first derivative, 4x cubed minus 16x, and second derivative, 12x squared minus 16. Now, right away, notice this is a quartic, so it's going to start in quadrant 2, possibly do a W, and then end in quadrant 1, because it's positive. Okay. The other thing I should notice is that I can take an x squared out of both values and be left with x squared minus 8. That means this has a turning point at 0, 0. So it's, and has a turning point when x squared is equal to positive 8. And when I take a square root of that, it's x is equal to positive 8 and x is equal to minus 8. Which means if I'm going to, see, I can understand this graph without the derivatives, which really helps. I'm going to have a w comes here, and by the way, that should be the square root, negative, negative. So at negative square root of 8 comma 0, it's going to come back. So it goes through, comes back, and it goes through, that's important, comes back, does the bounce there, that's what the squared tells me, and comes up here through square root 8 comma 0. So those are the 2 points, which means the critical points I'm expecting, I know one right away. But the critical points I'm expecting will be halfway between square root and 0 and negative square root 8 and 0. So that's important to know, just so that you can check for errors. So setting the first derivative to 0 will tell me those critical points. And notice that I can take 4x out of both, and I'm left with x squared minus 4 equals 0, which means this here tells me one critical point. And then this here, x squared is equal to 4, x is equal to positive 2 or negative 2. And that tells me the other 2 critical points. So I've got a negative 2 comma something here, and a positive 2 comma something here. And all I do is I put 2 back into the original equation to figure it out. So 2 to the cube, 2 to the 4 rather, is 16, is it? Yeah, 16. Minus 2 squared, which is 32. So get minus 16. And I'm going to get that for both of them, whether it's negative 2 or positive 2. That's because it gets squared n to the 4. So the negative 2 gets positive, and the plus 2 is already positive. So they're both at negative 16. So that helps a lot. And my other critical point I know is 0, 0, because when I punch 0 into there, of course I get 0. Now you can see that knowing the graph and analyzing the graph helped a lot. Okay. So now I'm going to just look at what we can discover. And what this book would want you to do is take a slope just to the left, and a slope just to the right, and a slope just to the left, and a slope just to the right to understand whether it's going down or up or down. Fair enough, I'm not going to do that. You go ahead and set minus 3 into your first derivative equation to see if the slope's negative. Then go ahead and set negative 1 to see if the slope's positive. Then put positive 1 in there to see if the slope's negative, and positive 3 in there to see if the slope is positive again. And that will tell you this shape. That's what the book wants you to do. Okay? You could also use negative 2 into this formula, and if it comes out positive, we're dealing with a minimum. So negative 2 squared and positive 2 squared are both going to come out the same. So I know the results for these 2 graphs will be the same, which almost automatically tells me they're both 2 minimums. And 2 squared times 4 times 12 is 48 minus 16, which is equal to 32 positive, which tells me minus 2 and positive 2 are both minimums. And when I put 0, which was my other critical point, into this equation, I get minus 16, which tells me that's a maximum, a local maximum. And that second derivative is very useful. I can also set it to 0. To discover that positive square root 4 over 3 is one of the x values, and negative square root 4 comma 3 is one of the x values, where there's an inflection point right there. That means where the graph slowly goes from one direction. The slope goes from changing directions. The way to explain an inflection point, you're on a ski hill, you're going down, it gets steeper, steeper, steeper. Then there's some point where your ski hill will get less steep. And that inflection point essentially is the slope changing directions, essentially. It was getting steeper, now the slope's getting less steep. So before it was getting more negative, and now it's getting less negative. And the second derivative tells you when that occurs. As it is, they want you to take points on either side to determine it. I'm not doing it. You can do that, and you will discover the slopes are the same as I determined. Now, obviously, some of these things you can't graph very well. Some of them you sort of can. For instance, this, I know the denominator is never going to get negative. It's impossible. So that means this whole result will be negative when the top is negative, and the top's negative when it goes on either side of 0, which means I'm looking at a graph that looks like this. And how do I know that? Well, because in the early stages when x is small, the results will go higher up based on this numerator. But as this parabola gets bigger and bigger, the result's going to get close to 0. The overall result's going to get close to 0. And you can determine this by realizing when x is huge here, this result gets very small. In other words, it starts to hug the y-axis. But in the early stages, the numerator plays a bigger role when x is 1, for instance, and it'll create this bump, which will create a local max on this side and a local min on that side. And actually, that's an overall max and an overall min. And that knowing this graph from that information helps. So the first thing I do, I have to take a derivative, which means I need to use the quotient rule. And using the quotient rule, the first derivative is this. Now that's enough to discover what I need to discover. If I want to, I can just set that equal to 0 and figure it out. But I'm going to expand it. And now I'm going to set that to equal to 0. And of course, the denominator disappears when it goes up there. So I'm really trying to find when is negative 2x squared equal to negative 18, which means when x squared is equal to 9, which means x at positive 3 and negative 3 are when these points occur. Now I go back and take positive 3 and put it in the main equation. And I get 6 over 18, which is roughly 1 over 3. Just make sure my math, yeah. And it'll be the same for the negative 3, because, except it'll be negative. And that's because that squared will be the same, and this will just become negative. So I'm dealing with the points minus 3 comma negative a third, and positive 3 comma a third. To determine that, all you do is see what happens at 0, what the slope is at 0, to see if that's positive, and to see what the slope does at 4 and minus 4. Doing that very quickly. So here's the formula for slope. You can ignore the denominator. So we're going to find out what the slope does. Actually, you can't ignore the denominator, because when you set it to a value, now the denominator plays a role. You're just trying, but you can see how long it'll take doing this method. So if I set this to 0, I get 0, I get 18 over 9, which is positive 2, which means my slope is positive going through this. Now that's good news, because it supports what I've drawn. Now I'm going to set it to minus 4. So I get minus 16 plus 18 up top, and 16 plus 9 down below, 25. And I can see I get a slightly, I probably did that wrong before. Yeah, it's negative 32, sorry. And I can see I get a negative number, which tells me the slope here is negative. And if I do it for positive 4 now, I get the same result, because 4 squared minus 4 squared is the same thing. So I'm dealing with negative 14 over 25. So that tells me both slopes are going down here and here, which tells me I'm dealing with a min and a max. As I said, you could take second derivatives. Now, in this case, second derivative is hard to take, because you're dealing with fairly complicated first derivative. And you'd end up being with something like this. And remember that that's squared. You'd have to take the derivative of this using the chain rule times the original formula up top. And you can see that second derivatives actually get all of that over x squared plus 9 squared, so to the 4. You can see that second derivatives for these things get super complicated. So in that case, you might want to use that method to take derivatives on either side, because second derivatives of first derivatives for rational functions are very hard. Not so for here, though. Not so for polynomials. So looking at this polynomial, first of all, I'm dealing with a cubic that's positive, so I know it's starting in quadrant 3, going up, and ending in quadrant 1. I also can see that there's nothing to be factored out. So the first derivative of this is this. Setting that to 0, I can factor out the 3x, and I'm left with x plus 2 to the 0. So I can tell you that there's a 0. At 0 is one of the maximum points, and at minus 2. So right away, I know my 0 is going to be my min point, and my minus 2 is going to be my max point, just because the cubic must climb up to the first point first and down to the next. If you don't understand that, realize that if a cubic is rising like this shape, the first point it reaches must be to the far left of the x-axis. Well, minus 2 is further left than 0. Therefore, it's going to max out at the first value that it reaches, because it must. Okay, so that means I just need to figure out what minus 2 is in this equation. So it becomes 12 minus 12, 0. So we can see that at minus 2 comma 0, which means that's a intercept point. Oh, wait a minute. I had to put it in the original equation up here. So I get 8 plus 12 plus 1, 21. So it's minus 2 comma 21. And now I punch 0 into the original equation, and I get, of course, 0 comma 1. Which makes sense. This one's much higher than that one. But if I'm going to figure out exactly what's going on, I will take minus 1 and put it into my derivative equation to see if it comes out as negative or positive. In other words, is it going down or up between this point and that point? So taking minus 1, I get minus 3 times plus 1, which is equal to minus 3, which means the slope is going down. Then I can take minus 3 in this equation to see what this slope is doing. And I get minus 9 times minus 1, which is plus 9. And I can see that slope's going up. Finally, I can take 1 on this side of this point to see if my slope's going up again. And I get 3 times 3, 9. So I can see my slopes going up again. Setting second derivative, so keep in mind this was first derivative there. Second derivative is 9x plus 6. If I punch in minus 2 here, I get minus 18 plus 6, which is a negative number, which tells me it's a max. And if I punch in 0 here, I get plus 6, which is a positive number, which tells me that's a min. So that's how second derivative. If I set my second derivative to equal to 0, I discover 9x is equal to minus 6. X is equal to minus 2 over 3. That means at x minus 2 over 3, I have an inflection point. So later on, you'll be able to learn how to map that inflection point. Might as well do it now. Yeah. Good enough. Oh, they just make you do it over and over and over again. Something I do like that they make students do it over and over again. What I don't like is I'm trying to teach you something new each question. So if I'm just teaching you how to do the question, and it's the same thing over and over again, you're not learning anything. So really apply the techniques I just did to just about everything. So they want the critical points, max or min, parallel to the horizontal axis. So, well, the horizontal axis is also has a slope of 0. It's y is equal to 0. So, yes, of course it will be. Here we're dealing with a reflection of a cubic. Here we're dealing with something to the 5 that's normal. Here we're dealing with a radical. And here we're also dealing with a radical. But be careful, the thirds are slightly different. So if you think of a cubic on its side, that's what you're going to get. To give you an idea, here is x minus 5. We'll get that up and running. Well, I might just stuck us in internet hell. Okay, well, let's just start with this one. And you know what we're going to take? Here's the main formula. We're going to take the first derivative. And we're going to take the second derivative, just for fun. Okay, so that's first derivative. Now we're also going to examine this graph a little bit. Since this has a reflection in the x-axis, we're now talking about a cubic that starts in quadrant 2 and ends in quadrant 4. That's what that reflection does. Okay, which means the first value I'm going to come across is going to be the min. And I actually, don't even have to really test it. You could get away with a test saying, because this is a cubic reflected in the x, the first value will automatically be a minimum. The only thing you would have to watch out for is that slip and slide thing, but I can tell this doesn't slip and slide. Okay, so let's find the critical points. So we're going to set I'm just going to put that down there for now. We're going to set this equal to 0. Oh, first of all, I'm going to take minus 18x out of both of them. And you immediately see the critical points are 0 and 2. Punching 0 into this, I get 0, 3. And 2, I get minus 6 times 2. Minus 6 times 8, minus 48, plus 72, plus 3. So that's 50 becomes 24, 27. Already I could see that that's higher than this. So that's also a way of instantly telling. And maybe that's all they want us to do, really. That means I'm talking about a graph like this. Comes down, it goes through 0, 0, and hits it doesn't go through 0, 0, sorry. It goes through 0, 3, right there, the y-intercept, and then it comes up here to 2, 27, and then goes down again. We don't know the x-intercepts. We'd have to do synthetic division to find that. Okay, you could also put the values you found in here, 0, into here, and you get plus 36, which tells me that 0 is a minimum. Sure enough, it is. And 2, when I put it in here, I get a minus 36, which tells me that's a maximum. You could also set this to equal 0, and you'll discover that x is equal to 1 at the inflection point, which is useful. So at 1 here, I get minus 6 plus 18 plus 3, which is 21 minus 15. So at 1, 15 up here, I get an inflection point where this slope starts turning around. You only ever have one inflection point on a cubic. We didn't really learn anything from that. So this is a power to the power 5 graph, which means it starts in quadrant 3, can do up to that many turns, and ends up in quadrant 1. You can have a maximum 3 inflection points, 4 turning points, and 5 x-intercepts, maximum. Okay, maximum. Taking the derivative of this, we get 5t to the 4 plus 3t squared. So that's first derivative. Second derivative is 20t cubed plus 6t. Second derivative. Setting first derivative, well, first I'm going to take a t, I should take a 5t through 2 out of it. And I get t squared plus 3/5 is equal to 0. Setting it to 0 now, I discover t0 is one of them. It's actually 2 of them because it's squared, so that means it turns right at that 0 point. If it was cubed, it would do a slip and slide. Okay, and this t squared also tells me it does a turning point. Oh, not necessarily, no. So now if I set this one, I discover something interesting. That is impossible. So that's interesting. So that doesn't exist. Let me make sure of my values again. So I'm going to set this to equal to 0. I get this. Divide by t squared on both sides. I get that. T squared is equal to minus 3 over 5. That can't exist. So that means that there is no turning point there. Interesting stuff. Let's get some more information here. First of all, when it's 0, it goes through 0, 0. So we know that that's going to do this. We also know it has to come back and go through the x-intercept again. Or not necessarily through the x-intercept. Yeah, through the x-intercept. And what does that mean? This one I might just have to graph. Oh. So that is what it means. Yeah, so this is a slip and slide, which explains why I wasn't finding an alternative value over here. Can't exist. So, to determine that, I would have had to take values on either side of this 0, and I would discover the slope is positive on both sides, which means that's not a critical point, but rather what I like to call the slip and slide. It goes through it twice. I think, could I have determined that? I'd have to find the roots here, and the only roots I would have found are 0, 0. And once I find that, I think I would know that it has to do that. If the only way one it crosses is that. I think just because the other critical points don't exist, that it must do that. And the only way you can determine it is to take values on either side, or you could take the second derivative. And here's the first derivative. And here's the second derivative. And when I put 0 into there, I get a 0. And because that's neither positive nor negative, it tells me the second derivative is also an inflection point. That's far more valuable tool in this case to see that it does that. However, I could have put 1 into this and discovered that it's 8, and negative 1 into this and discovered that it's also positive 8, and that with that double positive slope on either side, I would determine that it's not a max or a min. So when you encounter that, you can't discover any other critical points. Be aware. Okay, just really quickly, I wanted to show you what a x minus 3 to the 1/3 looks like. Okay. So it looks like a cubic turned sideways. And that's what the 1/3 does. If it was 1/4, it would go back to looking like a normal radical. And any even number up here would look like a radical. And any odd number will look like a sideways cubic, or 5 to the 5 or to the 7. Okay? So that helps to understand what it looks like. So looking at this one, to take the first derivative, we need the chain rule. And we get this. It essentially becomes negative x minus 5 negative 2/3 times 1, the derivative of the inside. So we can just ignore that. Negative 2/3 means it goes to the bottom. And becomes 2/3, which just means that we're taking this whole thing and squaring it. And then cube rooting it. That's what 2/3 means. Okay, now you're going to be able to tell almost instantly that something like this, the x minus 5 up here, we can see that the limitations are that when x is 5, we get a 0. So that means that 5, 0 is where we will have that point. Right here. And it also tells me that it's probably going to be not a critical point, because all these behave like this. Okay. So let's see if that's true. Let's set this to equal to 0, and we quickly discover that when this goes up, it becomes 0, and we get 1 is equal to 0, which does not exist. So we discover that there is no ever any spot where this has a flat max or min. We could also try to take a second derivative, but I don't think it matters. We could also say, okay, well, this is the only point I know of, and when this is 5, the whole thing down here becomes 0, and I get 1 over 0. So there is no derivative at that point. It's unsolvable, so instantly I know that that's probably going straight up and down at that point. Probably true for this one too, although I bet you the squared has a big impact. Okay, let's go on to that. So that one has no critical points. Makes sense. It's a cubic on its side. Now let's take the derivative of this. So I get a 1/3. X squared minus 1 to the negative 2/3 times 2x, which is the derivative of the inside. That's just chain rule, which comes out to this. Now there will be some conditions down here. We don't want a 0 in there. So that means that can never be 1 or negative 1. This is just the derivative though. Up here looking at this, we can find instantly that when x is 1, this thing is 0. And when x is minus 1, this thing is 0. So right away we have two two y-x intercepts, right? So drawing it right away, we discover that we're going to have a dot here and a dot here. Okay, so that's interesting. We'll also take note that there's no value of x in here. Oh yes, in between here, between those numbers, if that, let's say 0.5 gets squared, we get a negative number here, but no cube root's possible of a negative number. So that's fine. What it does in the middle is very interesting. I'm not sure what it does in the middle. Let's take 0 here. So you get negative 1, and the cube root of negative 1 is negative 1. So at 0, we get a little dot. Geez, does it do that? Interesting stuff. As this gets huge, the cube root gets tiny. So I believe it might cross. And then just hug. So I think it might have a max there, and a min there. And that min we just found is negative 1, 0. Let's test her out. So when we set this equals to 0 here, this goes away, and we just discover that x is equal to 0. Okay, so there's no maxes. This just will hug a value. And we discover that that's going to be a min point. When we plug it in, we discover this is the min point. You could take second derivative, sure, but let's just take values on either side, and I don't have to, because I can see when I took minus 1 and 1, I got x-intercepts. So that means the slope's going up and down on either side, so that's indeed a min. There's no other values for a max. Let's see what this looks like. Weird shape. Yeah, but at least we analyzed it correctly. So there's the x-intercepts. And this. And by taking the second derivative, we could see there was only one critical point. Strange looking graph. Looks like it has y is bigger or equal to negative 1 as a domain, and xer. Sometimes when this is, if this was a square root instead, in between 1 and 0, couldn't exist. See? That's because it would produce a negative number in here, and you can't take a square root of a negative number. But because it's a third, you can take a square root of a negative, or a cube root of a negative number. But a square would have created a no man's land in between. And that would have been an interesting one to find the derivative as well, because those technically aren't min points. They're lowest values, but they're not critical turning points. And that's that one. Yeah, well, okay, we just kind of did it. Oh, and they're running it through it again. So the only one that's going to be interesting, none of them actually will be interesting. Okay. Well, let's just go and try to struggle through them. I'm only going to go through 12 on this one. I'm not going to do them all. Certainly I'm not going to do the esoteric ones. Okay. Might not even do 12. It's got sort of like the missing value, but who knows. Okay, so very quickly, let's look at what we're looking at. Downward facing parabola. Parabolas only have one critical point. They want the critical point, local max or min, local min, or neither. Sketch the graph. Okay, so first of all, this is a downward facing parabola. Only the vertex matters. So if we take the derivative, we get this. If we set it to 0, we get this. Put 2 into there, we get minus 8, yeah, plus 16, plus 13, so 21. So we get 2 comma 21, and that's the vertex, and that's the max point. Okay, I don't have to prove anything more. I already know what this is. That's why I say that's kind of pointless. This one, we're talking about a cubic, right? So max it's going to have is 3 turning points. Or, yeah, sorry, 2 turning points. Okay. So which came first? So taking the derivative, I've got x squared minus 9. I set that to equal to 0. I get x squared is equal to 9. So that means x is equal to plus 3 and minus 3. And already I can tell you the minus 3 is the max and the 3 is the min. Has to be. Okay, so putting it in though, geez, do I have to bother? Let's just put it in the Desmos. Okay. There, okay. And see this point right here? First of all, let's take the second derivative, and we're going to set it to 0. And we're going to discover that that point right there is the inflection point. It's the point where the graph starts changing its slope. Okay, don't need to do more on that. Next one is also cubic. So we know the first one's going to be the max, and it's a normal cubic. It's got a positive lead coefficient. If you don't know what I'm saying, you need to study your cubic, your basics of your cubic, because you're going to save yourself a lot of trouble. Okay. So this is the first derivative. Set it to equal to 0. First of all, notice that it's a trinomial, and it's a parabola, so it could have potential 2 possible solutions, right? Which makes sense because we're dealing with this. So to solve it, you might have to take the quadratic formula or find something that multiplies out to 70 and adds up to 18. They're fairly far apart, 7 and 10. No, 72 rather. So you're talking about 8 and 9 and 7. Oh, 9 and 9 is 81. That would have worked. Let me make sure it's not 12. So you're talking about just let my quadratic formula solve it. So we're talking about, my brain's slow this morning. So we're talking about 72 and it adds up to 18. 36 and 2, 18 and 4, 9 and 8. It looks like it should have been it. So pulling up my quadratic formula, when I put in 6, 8, and 12, it's saying it doesn't exist. So that means that 18. There we go. So it did have results. Oh, of course. What an idiot I am. So that means that when x is minus 2 or x is minus 1, which one comes first? The minus 2, so that's the max, and that's the min. If you don't understand how I know that, study your cubics. It must come from quadrant 3. It must go up, it must go down, it must go up. Now the only other option is a slip and slide, which just says doesn't exist. Well, if it's not a slip and slide, then the first point must be a max and the second point must be a min. This is further left. Therefore the max must be -2 and the min must be -1. Putting -2 into this, you get -18 plus 36 plus -24. So you get, if I got that right, 4. So you get minus 8, I think, -6. And then when I put -1 into that, I get, yeah, I better make sure of my numbers here. And when I put -1 into that, I get -2 plus 9 my brain, -12. I get -4. Well, that should have been lower, but it's higher. How can that be? I did the -2 wrong, probably. So -2 into here becomes -16 plus 36 -12. Ah, I did do it wrong. So that's 24 minus 16. There you go. Plus 8. So it's -2 plus 8 here. And then -1 becomes -2 plus 9 minus 12, which becomes, oh, sorry, yeah, -1. And so that becomes -14 minus 5. So -1 comma -5. So those are the two critical points. That's a max, that's a min. You can tell from their y values as well. What a waste of time that is. Okay, what about this one? You're talking about a cubic that faces, that starts up here instead, goes down because of that. You're also talking about something that if I take -3x out of it, I'm left with x squared minus 5/3. And so I can tell you right there that there's a 0. And over here, so it crosses the x-axis twice. At the square root, negative square root of 5/3, 0, 0, and positive square root 5/3, 0, which means my max mins are going to be between those values, which is roughly, geez, it's going to be below 1.2, negative 1.2 and 0, and below 1.2 and 0. But anyway, in other words, it's not going to be clean. Taking the first derivative, I get this. Setting that to 0, I get this. Oh, there we go. It's a slip and slide. Can't exist, so it's not a critical point. It's a slip and slide. Minus 3x, and it goes like that. Minus 3x cubed minus 5x. Yeah. See? And actually, it's a slip and slide that probably has straight up, down, vertical, which is why you can't take a derivative there, because it's non-existent. So there's no max and mins in this one. Okay. And the derivative when it couldn't be solved tells you that right away. This is the same as is the same as this. Right away, notice that it's a sideways square. It's a square root of something. Could that possibly ever be negative? Okay, so just looking at it, you get x no, I don't think it has roots. Is that ever smaller than 0? And we'll just solve it. Taking the derivative of it, you get this. Over this. When you set the top to 0, you get this. Which means it looks like it has one critical point. When we punch that in there, though, we get what? 1 minus 2, so minus 1 plus 2. So you get 1 comma 2. The question is that the starting point? Let's take a value below that, 0. You get 0 minus 0 plus 2, so 0 is fine. Let's take a, that's an interesting point. When I square root a parabola, as long as it doesn't dip below the x-axis, if it's above the x-axis, and I square root it, these numbers are going to be small. I think I just get like a super stretched out parabola. As long as these don't dip. If this dips down, then it would be non-existent down here, and you'd get a starting point there. And we'll test that out as well. But it looks like this is above the x-axis, which means that that point that we discovered, 1 comma 2, is sort of the vertex. Let's try it out. Square x squared minus 2x plus 2. Yeah. So it's like a flattened out. I got this wrong. I did the subtraction wrong. It's 1 minus 2 plus 2. So of course it's 1 comma 1. But yeah. Now let's look at a parabola that does dip below. Okay. And I'll show you what I mean by that. So here's a parabola that does dip down below. And let's dip it down even more. Sorry, that doesn't show that it dips down, rather. We'll just keep that. This shows that it dips down. There. So here down where the parabola would normally exist, so I'll show you where this parabola would normally exist, and you'll see the connection. Okay, you see these points right here? After that point, this parabola went down below the y-axis. Therefore, the square root of those points can't exist. Which is why you have a sudden crash and burn right there. Right where the normal parabola would have gone across the x-axis. So all this zone here that's negative y values can't exist in the square root function of it. It helps to sort of know what this shape inside is going to be. And what about the last one? We're talking about a quartic, and I'm going to guess it wiggles through the line based on the one they gave us. Even if I take 3x to the 4 out of this, 3, I'm left with x minus 4/3, which tells me at 0, 0, something's going on, and then at 4/3, 0, something's going on. Okay, so just keep that in mind. Taking the first derivative from this, I get 12x to the cubed minus 12x squared. Setting that to equal to 0, first of all, I can take 12x squared out of both of them. I get x minus 1, which is equal to 0. And I discover that indeed when x is 1, I get a min point. and or a max point, and when x is 0. Now, because this, I believe we're going to have a weird wiggle thing going on. Okay, so when x is 1 and when x is 0. So plugging x is 0 back into this, I get 0, 0, which makes sense. And then plugging 1 into it, I get 1, 3 minus 4 minus 1. So that means I'm looking at something that comes down here, dips, comes back down, goes down to here, yeah, dips, quickly goes through, and then does that, I think. Yeah, there we go. So it sort of did a slide. So right there, I did some analysis wrong. And I should have seen from this, right here, when I take the 3x cubed out, this x cubed tells me it does a slip and slide through there. That was my mistake. It's finding the x-intercept here. When it's a cubed, if that's one of the x-intercepts, that's going to do a slip and slide thing. So this is the only min point. So that was the only part of my analysis that's wrong. This is not a max or a min. And you can tell that because this is the same graph. I'll just do the x and the 3 out of it. So same graph. And that tells you if that's a root, which it is, anytime you see a root that's cubed like that, it'll do the slip and slide. I believe it'll do it when it's to the 5 too. Yeah. So anytime you see, because it's sort of, if it's squared, it'll turn around at that point. See? But when it's cubed, it does a slip and slide through it. That's because squared means it bounces back. 1 just means it goes through it. And 3 means it does the slip and slide. And there's the only min that exists. And I should have spotted that. Oh, one of these puzzles here. It's giving us the derivative. And since this derivative is a cubic, we're dealing with something that's to the power of 4. We also know it starts here and here because it's a positive derivative. We know that at -1, 2, and -6 are the w points. I can also tell you, because it's a w, this one occurs first. This one occurs first, -6. This one occurs next. And this one occurs next. Which means, because it's a w, and this is the derivative, and it's a cubic, I started with the next to the 4, because this has no negatives in front of it. It means it's a positive x to the 4, which means it has a w shape, which means the first value will be a min, the second value will be max, and the third value will be a min. Now, you cannot find the exact values because unless this is the perfect cubic, the x4 could have had a number tagged onto it at the end, that would not have been in the derivative. For instance, if I have this, whatever, plus x, and suddenly I have a plus 27. When I take the derivative and get that, it totally ignores the 27. So we don't know the exact graph it came from. But if they're saying that, yeah, this was the derivative, what I would do is expand it first. They said this was the exact derivative. What I would do is expand it first. And I would get this. However, this last one is wrong. It would have to be a... The first ones would be... Let's see, sorry, x squared minus x minus 2. When I multiply that by x, I get x cubed minus x squared minus 2x. I'm going to multiply that by 6. I get that, which means this is the full-on derivative. And if I go backwards from that, it would be dealing with something like this. Okay, so when this comes, oh, sorry, this would be minus 4. This would not be 15, this would be 5 over 3. And this is accurate. See, when this comes down, these would nullify and create that. When this comes down, they'd cancel out and create that. When this comes down, it would create that. And when this comes down, it creates that. But what you're missing is a mysterious possible number here, which would not be in the derivative. But if they're telling me that the derivative is pure, then I could then take my minus 6 and plug it in, and my minus 1 and plug it in, and my plus 2 and plug it in and come up with the points. However, this is not always the exact original formula of that derivative. That derivative can be the derivative of many different x to the 4 graphs. However, I will tell you that the minus 6 is indeed the minimum, the plus 1 is indeed a max, and the plus 2 is indeed a min. No, I'm not doing that. That's a pointless waste of my time. If your teacher's going to give you puzzles like that, work with him and do it. I don't have all of 10 here. I've cut it off. So here they've given me a parabola, and they want me to determine A, B, and C. Well, you got a lot of information there. And they're telling me it has a max there, so I know it's a negative parabola if that's the max. I can also tell you right away that I could come up with the derivative, the vertex formula just from that. With an A value, and now all I would have to do is use one of these points to figure out my A value. Let's see if I'm right. and do it the simple way. So 0, 1, I put the 0 in for x and the 1 in for y. And I get a minus 3 squared plus 12 is equal to 1. So I get 9a plus 12 is equal to 1. 9a is equal to minus 13. Probably not. Let me see, relative maximum. One of the minuses, right? X minus 3 plus 12 is right. And that's a point on it. So I can take that for 1 and that for 0. 9. So far, so good. Oh, I got it here. It's not minus 13, it's minus 11. So a is equal to minus 11 over 9. Which means I could now expand this up here. That's just this a, it's not the real a, okay? So we get here, this expanded to become x squared minus 6x plus 9 plus 12. But I have first I have to multiply by minus 11 over 9. So I would get minus 11 over 9x squared minus 66 over 9x, and then just minus 11 plus 12, which would be plus 1. Simplifying it here, there's no simplifying that. This all divided by 3. And then that's just 1. It doesn't seem like they would give that to me. Let's see if we can do it using their methods. So, this is a max, which means when x, the derivative of this, let's take the derivative of this, is equal to 0, we know that the x value here is 3. So right away we get 6a plus b is equal to 0, and we have a formula for b. b is equal to minus 6a. So that's the first bit of information. The second bit of information they give you is that when x is 0, y is 1. Because that becomes 0. So we also know that c is equal to 1, a is equal to 1 minus c. So that's the second bit of information you have. And finally, the third bit of information you have is that this. When y is 12, x is 3. And therefore you have a third equation. And when you have 3 missing variables and 3 equations, you can solve it. Let's first solve it by putting in this value of b and this value of a, and we'll solve it. So you get 12 is equal to 9 times 1 minus c plus 3 times b. Oh yeah, no, let's solve it one step at a time. So first you're going to solve it with putting a into here, and you get b is equal to 6 minus 6 times 1 minus c, which is minus 6 plus 6c. And now that you have a value for c for a and for b, you can substitute it in here, and everything will become c. So you get 12 is equal to 9 times 1 minus c for a, plus my new value of 3 times b, which is minus 6 plus 6c, plus c. And then if I expand it, I get 12 is equal to 9 minus 9c minus 18 plus 18c plus 1 more c, so plus 19c. Adding up all my terms, 19c minus 9c, I get 10c, and I get 12 plus 18, 30, minus 9, 21 is equal to 10c. So I think I might have done it wrong. But you get the idea. Once you have three equations to represent three numbers, you can solve, if you're missing three variables and you have come up with three separate equations, you can solve them for it. I think they picked really funky A, B's, and C's here, though. I could go back and do it again, but that's the general idea. Oh, no. No. It's the same thing again. Okay, well, I'll try 13. So again, taking the derivative of this, we know that 3a x squared plus 2bx plus c is the derivative, and when it's equal to 0, x is 2, and when it's equal to 0, oh, we also know that too. So when it's equal to 2 and when x is 0, this is true. So you could find two different variations from that. Then you can plug it into there and there twice to get two formulas for d. For instance, when x is 0 here, these all disappear and it's saying y is 0. So that means right away d is 0. So d doesn't exist. Okay, so that helps. Oh wait, no, that's just a local min. Okay, so you have to find the points first. More work than I want to do. Let's look at 14. Why not just ask math questions? I get that they're trying to be clever, but I get that that's a math question, so I shouldn't really say that, but whatever. I'm not here to do endless solve for ABC. For each following graph of fx, make a rough sketch of the derivative. By comparing the graphs of fx and show that the intervals correspond. Okay, so that's just showing that where the derivative match. So that's a line. So you can tell that it's going through, you'd need to find, so it's going through 0, 1, and 2, 5. So right away I can tell it's 4 over 2, the slope is 2. So that means the derivative is this. Y is equal to 2. And that's just saying that the slope is always positive, and it's always positive 2, right? This is a sine curve. Let's go to this one. This is a parabola, which means the derivative is going to be a straight line. And it's going to be a straight line that crosses right through there. And that's because when it's below the y-axis, the slope is negative. And when it's above the y-axis, the slope is positive. Oh, sorry, I got that reversed. It's this way. So the line, when it's positive y, it's showing that the slope is positive. When it's negative y, it's showing that the slope is negative, and this will represent the critical point. I might not have the exact slope of this line. To do that, you would look at the fact that it crosses through 4 and minus 2, and therefore has this as values. And you'd also have to look at the fact that its vertex is 1, 2. And you can come up with the exact parabola from that, because you have 2 points and the vertex, or 1 point and the vertex. So you know that in the vertex formula it would be this. And then you can just set your A and B, your X and Y rather, to let's say 4 and 0. 0 and 4. So it's going to be equal to 4 when this is 0. Sorry, it's going to be equal to 0 when this is 4. So you get 9 times 3, A times 3 squared, which is 9, plus 2 is equal to 0. So you get 9A is equal to minus 2. Therefore, A is equal to minus 2, 9. So once you have minus 2 ninths, you can figure out the formula. Or you can expand this and leave A like that, and you get x squared minus 2x minus 8, and all of it times A. Right? And then you can just set that, because you know the vertex. You can set that when x is 1, y is 2. So that's going to be equal to 2 when this is 1. So you get A minus 2A minus 8A is equal to 2. You get minus 11A is equal to 2. So A is negative 2 over 11. So now you have the exact formula and you can figure out the exact line. But the line I drew is pretty damn accurate. Okay, the derivative of a sine curve is a cosine curve. And what you would look at here is you would say, okay, at this point here and this point here, the slope's positive. So that means we're dealing with something that is above the y-axis there. And then you'd say this is negative. And then you would say this is negative. And you're going to discover that this is a good representation of the slope of that. And you're going to discover that the derivative of the sine curve is the cosine curve. Okay, this is the actual function. So that means a cubic is going to be the thing. You'll see that it's a negative slope right to there. So that means negative, yeah, so that means we're coming up from here. Well, it goes down there. Yeah, so from here, positive, and then negative again. So that's going to be the point where it crosses. And that's going to be the other point where it crosses. So right through x represents where that critical points are. And you'll also notice that when this graph here is negative, the slope is negative. And that when this graph here is positive, the slope of this graph is positive. And again, when this graph here is negative, the slope of that thing is negative. And that's how you come up with a graphic representation of those. They're doing it again with ABC. No. So good luck. And that's it for that section. It's a stupid section. It's too many ABCs that have nothing to do with derivatives.